Good evening, Nishant sir.
Good evening, sir. Good evening.
So just sir, we
Yeah,
can
yeah,
5 minutes,
will
sir.
wait. Yeah, sure. We will wait 5 to 10 minutes, then we'll start. No issue.
Okay, sir. Thank you, sir.
Okay.
Good evening, sir. Nishant, sir.
Good evening, sir. Good evening.
For participant, I want to introduce about sir. So, today, very healthy good evening to all of you. Just wait 1 second. Okay, healthy good evening to all of you for today 6th session of ATAL FDP program, Hybrid Microgrid Opportunities and Challenges for Renewable Energy Resources. I am Dr. Shivam, Assistant Professor of Electrical Engineering Department, NIT Kurukshetra, co-coordinator of the ATAL FDP. Heartily welcome Chief Guest of the Day, Dr. Nishant Kumar, Assistant Professor, Department of Electrical Engineering, Indian Institute of Technology, Jodhpur, Coordinator of the ATAL FDP, Professor Ratna Dahiya, co-coordinator of a School of Renewable Energy and Efficiency, Professor in Electrical Engineering Department, NIT Kurukshetra, and the faculty members and participants of the event. The primary objectives of the ATAL FDP is to provide a national forum to the faculty and research scholars to share the basic knowledge with an objectives of understanding the concepts, aspects of penetration of renewable energy sources, electrical vehicles, and with hybrid microgrid operation. Now I would like to address of today's session speaker, Dr. Nishant Kumar. Currently, he is Assistant Professor, Department of Electrical Engineering, Indian Institute of Technology, Jodhpur, India. Before joining IIT Jodhpur, he was a postdoctoral research fellow at the National University of Singapore in the Department of Electrical and Computer Engineering. He has completed his PhD from Indian Institute of Technology, Delhi, India, in the Department of Electrical Engineering, where his PhD thesis was awarded with the Best Thesis Award. His PhD thesis also won the first prize in IEEE IAS Thesis Contest 2020. Moreover, during his research, he has received POSCO Power System India National Award in doctoral category and IEEE's PhD Thesis Award 2020 at IISc Bangalore. He has completed his MTech from NIT Durgapur, where he was awarded gold medal for his research work in front of the President of India, Sri Pranab Mukherjee. In between his MTech and PhD degree, he worked as the project engineer and research associate at IIT Bombay and IIT Delhi. He has completed the BTech degree from Silicon Institute of Technology, Bhubaneswar, India, where he was awarded as the best technical student. Recently, he has been facilitated by IEEE as IEEE senior member and by the DST Government of India with Young Scientist Award for representing India at the 5th BRICS 2020 Young Scientist Conclave held in Russia. Additionally, he has received the Outstanding Young Professional Volunteer Award by IEEE India Council. He is a fellow member of the Institution of Electronics and Telecommunication Engineers IETE Society and editor in few IEEE transactions. He has more than 60 publications, including 30 IEEE transactions and 8 Indians and US patents. His areas of research interests include optimization, algorithm development, renewable power generation, microgrid, a smart grid, and application of adaptive control and optimization in power and energy sector. Welcome, sir, for today the session. Thank you, sir.
Thank you, sir. Thank you for this long introduction. So now I'm sharing my screen and then we will start.
Yes, sir. Thank you, sir.
I hope my screen is visible to everyone.
Yes, sir.
Okay. So before going to start this session, first of all, I'd like to thank all the coordinating members and the volunteers related to this FDP. And a special thank to Professor Ratna and the Dr. Shivam for giving me this opportunity to interact with all this audience. And in this FDP and today's session, mainly I will discuss about AI-based control. So, and definitely this control I will discuss, what control I'm going to discuss. This will link with the solar and I will discuss related to the solar. But on the place of solar, we can go with the different one also. If you like, you can go with the wind. If you like, you can go with the tidal, whatever. So only a basic component will change. The rest, all the components will same. So I will point out all those things also. But how and what is the use of this AI-based AI-enabled control and what are the challenges we will sort out, and those things I will discuss today. So, so first of all, the layout. Definitely, this entire session is based on the microgrid. So, the first of all, I will start from the basics one, and then I will come with the actual program. So, in this today's discussion, the layout is very simple. I will consider a solar panel, and then this solar panel I will integrate with the grid, and in between I will consider a single converter or maybe two converters, and then some local loads. And then here, what are the challenges we have, and how we can sort out. So those things I will discuss. So this is the basics layout. Here I'm not going to consider any storage and all, because here the consideration is my grid will behave as a sink and source for me, right? So it means that whenever the generated solar power will be, or generated power, whatever source you are going to use, maybe wind and all, whatever source you are going to use, if your power is more than your local demand, so extra power you will fed inside the grid, and that time grid will behave like a sink. Same time, when the generated power is less than your local load demands, then you can take the extra power from the grid and fulfill the load demands. So that time grid will behave like a source. So this sink and source behavior I consider with the grid, right? And so this is the consideration. Okay. And if you will go for the classifications, so what are the system classifications we can consider? Then we can go with the standalone side, means the no grid, only the local loads in the system. Another is the grid connected interface. In the grid connected also, we can go with the single phase and three phase. It will depend on the power ratings mainly for the small power system. So for example, rooftop solar power, the best suitable is the single phase. But your power rating is higher, sometimes 20 kilowatt and more than that. So you can choose the three-phase system also, and like that. In the case of three-phase also, we can choose the three-phase three-wire system and three-phase four-wire system. That's it. If you will think about the control side, I will say only the inverter size is going to increase. The control side, the DSP based or digital control side, so not you will not see any bigger changes. Only minor changes you will see in your pulse generation, nothing else. Rest all will be almost same for all those systems. But yes, the converter will increase with your different consideration. For example, in the single phase, you will see the two leg, means the four switches will be in your inverter, integrated inverter. Similarly, in the three phase, you will see the three legs in six, and the similarly three phase four wire, you will see the four legs and the 8 number of switches in that. So like that, this it has classified. And again, the connections. If you will go with the input side connections, with the source side connections, maybe single stage and two stage, both. Single stage means suppose you are going for the wind, so the wind generator will directly attach with the inverter and then attach with the link grid. So this time, you can say this is your single stage. Means the source directly attached with the inverter and then the inverter attached with the grid. But at the same time, you can go with the two-stage, means in between the source and then inverter, one another DC converter will use, and that DC converter will lift your DC voltage and try to match the voltage requirement, DC voltage requirement on the input terminal of the inverter. So that is two-stage. I will show that how this works. So like that. So we can again classify based on the stages, power conversion stages mainly, you can say that, right? And the next classification, you can also go for the inverter, panel configurations or the inverter configurations also. On that based we can classify. For example, you can say the string inverter side or maybe micro inverters. String inverters means all those solar modules or solar array will connected with each other through the in parallel or series, you can say, but at the end all those series and parallel combinations of the different modules will attach with a single inverter. So this is your string inverter arrangement, you can say that. Another is micro inverter side. Micro inverter means a group of, this is here in picture it is shown one, but you can say this is a small group of panel attached with one inverter, second group attached with the second inverter, and like that. Both have one merit and one demerit. So if you will look about, if you will think about the losses, switching losses, converter losses, inverter losses. So here in this case, the loss will be lesser with respect to this, because here the number of switches are more, the inverters are more. So the losses will be more here, but with respect to this one. Right. So, but another merit here is the reliability side. If you consider on the reliability, then you will see this type of system is less reliable with respect to this. Means that in this system, suppose your one switch is gone, one switch is not working, then what will happen? Your entire inverter will shut down, the entire power plant will shut down. Right? But here, if your one switch is not working, so this one small group of solar panel will not in use, rest all will be used, right? So this is the thing. So the reliability side, this type of things is more reliable, and also it will depend on the rating mainly, I will say. So if you have a 1 megawatt plant, 2 megawatt plant, and 3 megawatt plant, so if you will try to find out a single inverter for 1 megawatt rating, definitely this is not possible. Here definitely required a series of inverters in parallel combinations. So this is the limitations of the semiconductor switches. So for a bigger rating, for higher rating, definitely the micro inverter is a single option for us. But yes, for the lower rating, small rating, we can go with this type of thing. And if I will consider on the uses side, so I can say for your single uses, for your residential uses, for your rooftop solar panel, this one is the best option for you, right? But for the commercial users, means if you have a PV park and all, you are generating power for the commercial level and trying to feed in the grid and earn money, that is your prime objective. So on that conditions, this is your best option for you. So this type of things we can. But yes, again, the control side, control will be more or less same, nothing else. Here definitely we have the 4 inverters, the 4 DSP you will see, 4 control. Control will dump in the 4 DSP kit, and then all the DSP kit will operate one inverters and like that. But in this case, you will see a one single DSP and that will operate this inverter and like that. The classification, if you will go think about the based on the control side, then again the 2 part you will see, one for the source, one another for the grid side. Means we have the source. Suppose the source is solar, or we can say the source is wind or anything else. So the maximum power extraction from that source, because the source is renewable based sources, so that is your main task. So this is your source side objective, you can say that. Power extraction from the source, whatever source we are going to consider, that is that. On another side, the grid side, we are going to integrate with the grid and fit the local loads. So this side, you will see the grid code matching, or we can say the grid synchronizations objective matching is your secondary, or you can say the second objective. Grid code or grid side matching means grid voltage, grid frequency, grid phase, all those, right? As well as the quality of the power, what we are going to dump inside the grid, right? So these things. So this is a second set of objectives for the on the output terminal. We can say this is for the output terminal objectives. In the 2 stages, you will see the 2 converters. So the first objective will fulfill through the first converter that will be closer to your source, and the second set of objective will fulfill through your second inverter, which is closer to the grid in the two stages. But if you, in the case of single objective, single stages, both objective will fulfill through the single inverter. That is okay. So these are the basics things. But now I'm coming on the actual picture and actual issues. So in general, you will see, suppose I'm going to work with the solar. So you will see that the solar panel generates power, and then all generated power is using on the local, and then all the rest power going in the grid, right? So this type of system you will see, right? But here in this system, when the power is generating and going in the grid, so this system works for how much duration? If you will calculate the duration, then you will realize more or less it will start working from 8 a.m. morning and it will go till 5 p.m. It means around 8 hours the system will work, right? And the rest 16 hours, what is the use of the system? The system means the panel, all these converters, and all these things will not in use for the 1/3 period of time. Okay. So you can see that if those things are not going to use, so because that time we will take the direct power from the grid and fit to all our local loads, all the converters and all these things will be not in use. So around 2/3 duration, you are not going to use your system. So you are not going to use 2/3 duration, means like 15 to 16 hours. So on that basis, we can say utilization factor of the entire system is around 1/3, because the only for the 1/3 duration it is going to work. So we can say the utilization factor is around 33%. And again, this is not 33%. This 33% we can say only when the solar irradiance is constant and this is on the maximum level, which is not possible. Definitely the solar radiance will increase slowly from 0 to 1000 watt per meter square and then again come back to 0 and like that. So the solar radiance will change with the time, right? According to the solar conditions or the climate conditions. So the solar radiance will change. So we can say the solar irradiance is not on the maximum level, but or on the peak level, but the plant is designed for the peak level, right? So here the utilization will again further decreases. So more or less, if you will think about the utilization factor of the plant is around 20 to 25% is the utilization factor. So, and this less utilization factor is a very bigger challenge. Why I'm talking about the bigger challenge? Because if you look on the network, this is the network. This is the actual network. This is the panel. Here you will see a DC-DC converter, another costly capacitor you will see on the DC link, then again one inverter, and these are the filters. In the night, I'm talking about the not working. It means 2/3 duration. In this 2/3 duration, also you can say that during the night time, this system is not going to work. This entire system is not going to work. And nighttime, or you can say at that time, the load will directly take power from the grid and operate accordingly. But the question, how we can use this system in the nighttime? Is any way we can use this system in the nighttime? Definitely, I'm not telling that the sun will come in the night and we will generate, because we all know the sun will not come. So, but in different purpose, we can use this or not? The answer is yes. We can use this small section of this circuit, we can use in the night as a STATCOM or DSTATCOM. According to the conditions, we can use that. Means that in the night time, this converter and these filters and control and this capacitor, we can use as a STATCOM to generate reactive power and support the grid, or we can use as a DSTATCOM to generate the nonlinear currents for the local loads and support the grid. So means that in the night time as a STATCOM or DSTATCOM, we can operate the system and support the grid, right? So this process we can do that. And here the change of the mode will not based on manual configurations, it will based on the automatic system, right? It means when the solar radiance will not sufficient for as a plant, so that time the mode will change and it will behave like this way. But in the other time when the solar radiance will sufficient solar radiance is on the panel, so the generated power is capable to convert in a accurate manner. So that time the control will change from one mode to another mode. The first mode is the plant mode, means where the solar power will come and go inside the grid. The second mode is in the night time, it will behave like a DSTATCOM or STATCOM. So we can configure the system in this manner in the night. So through this way, we can utilize the utilization factor of the system. So this is the first objective, first extra objective, which we can include in the system for night. Another one is the nowadays, as we all know that we are going to play with the electric vehicles. Means the vehicles are going to come in the market, and everywhere you will see this type of arrangement, means the charging arrangement. So here, if someone going to charge electric vehicle by using any I will say the standard charger, then no issue. No issue with the charging and no issue with the electric vehicles. And that time the electric vehicle is just a load, that is AC load or DC load according to that, according to the charger charging power rating, we can say that. No issue with that. But at the same time, if someone not going to use the standard charger, because the standard charger will be definitely costly. So definitely, so someone will, if you're going to charge the electric vehicles by using the low cost cheaper charger, then what will happen? First of all, what is low cost charger? Low cost charger means what? You want DC here. Input is AC, grid power is AC, you want DC. So how you will do that? Simple is that by using the diode rectifier and here one capacitor, you can see here output terminal, you will get the DC. And since you have a sufficient amount of the bigger capacitor, so here the DC output will be very good in nature, you can say, not that much pulsating, you can say. And also if you want to match the voltage here, so by sometime you will see one transformer here, a small transformer, a step down or step up transformer to match the voltage. So this is your most cheaper chargers. Ideally, which not should be in the market, but yes, this will. So this will, because this type of chargers will become in the market. Not, I will say, not come in the market, already existing in the market. For example, so many local cheaper mobile chargers are available in the market. But that time, this is not a big issue. What is the issue here? Issue is if you look on the output terminal, because you are thinking for the output. So here on output side, you are going to attach your battery. Here you will get the UDC, no issue. But the same time, same charging side, when you will see here on the input terminal, current waveform. So this is your current waveform. This is your current waveform. And now you can realize this pulsating current means a heavy harmonics you are going to introduce in the grid. So this highly harmonic current you are going to introduce in the grid because of this type of network. Right? So this is the things. So in this system, and I will say this is nothing new here. So many mobile chargers are already available based on this circuit. But currently we are not talking because the mobile charging current is very less. So on the output terminal, less than 1 ampere you will see. So here is 1 ampere. It means here you will see less than that, right? So that is not a big issue. Milliampere current or some 1 or 2 ampere current, and the corresponding harmonics are not that much significant. So we can ignore, right? But at the same time, if you are going for the electric vehicles, then that time this current will be not 1 ampere and 2 ampere. That time here you will see the 10 ampere, 20 ampere, sometimes 100 ampere. And if you are thinking for the fast charging, ultra fast, so that time the current rating will be around 500 and 1000 amperes also. And these diodes are also available for those current rating. No issue with the diode also. The diodes are already available for those ratings. So those type of chargers are going to come in the market. And that time this harmonics is a very serious issue for our grid. Right? So these things we can sort out. This issue we can sort out through introducing a rheostat behavior inside this converter control. Means day or night both. I'm not talking about only the night, daytime also. When the solar power is generating, so that time whatever power will come from this side, and we will try to push inside the grid. So that time what we will do, we will check the behavior of the load. So if the load wants heavy harmonic currents, so we will generate that amount of current from this converter. Means this converter will generate that harmonic current for my local loads, and that will go through this terminal, so that the burden will not come on the grid in the daytime also. In the night time, definitely when the solar is not there, so that time we will generate only reactive power, not only reactive power, only harmonic current for these local loads and fed to these local demands. So this behavior also we will include in our control. So these two issues will be day and night will work in that. Now come on the control side. The control is very simple. So mainly this all the control means what? The power management. Simple. In simple word we can say this is a power management. Power management means what? The power is coming from this side, so we can say this is PV power. Power is on this terminal coming and then going towards this side, means this is a load. So the power is going towards the load. So this is the load. And generated power minus load, if you then you will see this is a positive or negative. Means the if generated power is higher and load demand is lesser, so that time you will see this is positive. The difference is positive, then that time you will see the power will go inside the grid. If this is negative, means power will come from the grid. Simple. So power. The third is here, so many switches and then filters and the interfacing inductors we have used. So this component is not an ideal component. So definitely some losses you will see. So those losses, we can say that is also a load, because loss means what? Power is going. So we can say that load. This is also a type of load. Right? So the control behaviors is based on this power management. So the terminal, the PV power is coming on the PCC. PCC means the point where all the components are connected. That is PCC, point of common coupling. Means the PV power is coming. So we can say this vector is coming inwards. So this is PV power. And then we have the load. So this is the load power. Power is going outwards. So this is outwards vector. As I told, so one another load is all those losses. So losses on the DC link, losses across the switching, losses across the filter, all we can consider here. So this is the loss component, we can say. This is also a type of load. Power is going outside, right? And then we will see after that. So this is a coming power and these are going. So after that, this is positive or negative. So according to that, this will decide. So that's why here you will see the bidirectional nature of the arrow. So this is your grid power. Power will go inside the grid. So that will be the grid is going to behave as a sink, and power is coming from the grid. So that grid will behave like a source. So these all are the powers: load power, PV power, this grid power, so losses power, and the grid power. All are the power on the PCC. This PCC, on this PCC, you will see grid attached, right? Grid attached. So if grid is attached here, and we know that the grid voltage is constant, right? So grid voltage is constant. So if grid voltage is constant, so what will happen means the grid power, if you want to increase your grid power, decrease the grid power, and voltage is constant, it means what? It means your current components are going to increase or decrease according to that, right? So what we will do, so this if this voltage is constant on this PCC, so we will divide this power to the voltage, this power to the voltage, and this power to the voltage. So all these power component we will divide to the voltage. So what you will get? If this power will divide to the voltage, then you will see the equivalent current component. There is also, you can say, the PV current, equivalent PV current. Similarly, if this is load power and divide to the voltage magnitude, so what you will get? Load current magnitude, you can say. The same, this voltage, if you will divide here, so you can say the grid current magnitude. Similarly, this losses, this loss power, if you will divide to the voltage, then you will see the DC loss current component, and like that. So all those power component will convert into the load current component through the dividing to the voltage. So finally, we can write this equation in this manner. So this is IDPV, means the power PV side, the current is coming. This is that one, and these are going. So minus beta DC minus zeta LP. So these two load and the losses is like that. And then after that, it will decide if this is positive, then go inside. If negative, it will come from that. So this is your zeta PV, and this zeta P is grid current magnitude, right? So this is the basics of the any control, whatever controls you want to introduce. So right, like that way this works. Here, before going to come on the actual control behavior or control manner, control technique, first of all, we will see why I'm talking for the AI-based control. When we have lots of several control, you can say the different type of controls are already in the market, right? So already available on the commercial level, but still I'm talking about the AI. Problem is, so many robust controls are already in the market, but everywhere you will see some some delay, some lagging, and these things are available in the control behavior. And you know these components are AC in nature, right? And AC in nature, and as I told, so we are going to play with the heavy harmonics on the PCC, on the attachment, on the load side. So the here the estimation should be very accurate. If you are capable to estimate those harmonics accurately, then only your control is going to work accurately. Error will directly impact on that. For example, suppose here what amount of the harmonic demand is from the load side, and if you are going to estimate, and suppose just assume your estimation error is 1%, and in case one, I'm just assuming your estimation is a little bit higher, means 1% higher with respect to the load demand, then what will happen? If the 1% higher load demand and mainly about the nonlinear current. So if you have 1% error, so this inverter will also generate 1% higher harmonic current, right? And then that extra current will come on this terminal. This terminal is PCC. So one extra current will come on the PCC, but the load will consume exactly according to the load demand. So the extra 1% will go where? Inside the grid. Means you, because of the overestimation, the extra nonlinear current is going inside the grid. Means you are polluting the grid. Second side, just assume you have estimated but estimated less than 1%. Then what will happen? Inverter will generate less than 1%, come on the PCC, but the load will consume according to the load demand. It will exactly be according to the requirement. So the next extra 1% will come from where? It will come from the grid, because grid directly attached here. So 1% extra harmonic will come from the grid. Means error will directly impact on the grid current. If your estimation is positive or negative, whatever, both conditions, grid is going to face, the grid is going to face, right? So this estimation is very important. And the delay in the control network is the bigger challenge here, because this is AC circuit, this is not a DC circuit. It means that on every moment the signal is changing. If you have a one stage delay, means your estimation and your action has one step delay. And what you have estimated and what you are going to face, that time definitely you are going to face some error. So how we will overcome those things? So that is the challenge. Otherwise, these controls are very good if you are thinking for the normal operations. But here we are going to sort out those issues. So how we can do that? So for that purpose, I am going to discuss here a ANOVA-based kernel stochastic gradient descent based algorithms. So this ANOVA kernel stochastic gradient descent algorithm means this ANOVA kernel trick has attached with this stochastic gradient descent algorithm. So ANOVA kernel trick means this is a mapping technique. This mapping technique means normally what happens in adaptive control, you will see, so first of all, we will take an action, then we will see the error, and according to the error, we will retune the algorithm. That is adaptive in nature, right? So we will retune the algorithm and then again take the action, then we will recalculate the error, and then again we will tune. Again check the error and then retune like that. So this is the adaptive behavior. According to the error, we will retune, right? So this is the adaptive nature. But in this algorithm, what we are going to do in this system, we will include the ANOVA kernel trick. So what it will do, it will see the errors. It will see the errors and then try to predict the error for the next step. Here we are not going to predict the action, as well as we are going to predict the error for the next step. And when we will going to retuning or going to update our action, so that time this updated error will consider, right? And like that way. So here we are trying to sort out this error in advance. So this is the main concept here. And for that purpose, this ANOVA kernel trick is attached, and this is your single layer neuron structure. This is based on the neural networks, but this is single layer neurons. So beauty of this single layer neurons means not required any prior training, not required your system ratings. One control will work for every type of system, every types of rating, because it will not depend on that and not required any prior training set of data and all. So you can use everywhere. So this is the beauty of this control behavior. So here you will see, suppose this is the load current and this is your filter, and then here you have estimated this component. Then at the end, we will calculate this is estimated one and this is the actual one. What is the error? And then according to the error, here we will analyze the errors pattern. And according to the error pattern, we will update the weight, and then adaptive filter will take the action, not according to the error, here according to the forecasted error, or you can say the predicted error for the next, or an error for in advance. So this way, this will update. So this is the actual picture of that. And this is your single neurons. So not required any library, not required any tuning, just data, error, and then error will go through that way. So this type of things you will see that. And then here, mainly this is equations and calculations, right? So the basic equations and calculations are just like your functions, and then function is the function of load current. This is load current. Sometimes you can take the grid current, which component you want to filter out, so that component you can take here. This unit template means this is a pure sinusoidal signal, and this is your updated weight, you can say that. This comes from the ANOVA kernel, right? So here in this equations, you will see the predicted error. So here we are going to predict the error and this predicted error, and then we are going to update the weight. This weight will depend on the errors as well as this ANOVA kernels. ANOVA kernel is an advanced functions. So these things you can see this way. The ANOVA kernel function is like that, and in this relationship, what relationship we are going to do here? Mainly we are trying to establish the relationship between the errors. So that's why you will see the auto correlations and adaptive design parameters. So finally, we are trying to create a relationship between the error pattern and then try to predict the real errors or actual errors in each step. So like that way. So this plane finally going to converge towards the actual error. So this type of things we will do here, right, in this control. And these equations, the set of equations are for the for phase A. So you will see everywhere suffix A, but same thing we will do for the phase B, same thing we can do for the phase C, and according to that. Suppose this is a single phase system, then only phase A will be there. If it is a three phase, then like the phase A, B, C will be there, like that. So implementation side, we have the two options. One is if you are going with the DSP, so simple, we can code this one inside the DSP, and these three will be required. The input terminal, you will see that these two terms, right? These two will be the input of this, and then rest will be the rest is a calculation. So we can calculate accordingly through the code, nothing else. And also this UC means the grid voltage. I will discuss how this UC will calculate from the grid voltage. That's it. Means the grid voltage, and then your load current is enough for run this code automatically. No issue, no further other information is required here. Right? This all is the calculations and related to the interleave. Yes, but here you will see some constants and how we will tune the constants also. So in this calculations, you will see the 1 omega is here, and this omega is the constant of this technique, and this is called the learning rate. And how we will decide the learning rate, actual learning rate, real values. So I will show that. So through the stability analysis of this system, we can do these things. So that is the one way through the coding. Also, you can go through the block diagrams also. That same mathematics through the block. Also, we can do that. Nothing else. Okay. So the question was the omega, how we will decide the value of omega, and for that, because algorithm parameter is a very challenging thing, and to decide that, and that is the important for the stability as well as the performance. Right? So for that purpose, what I have done, the same equation, same set of equations. This is the predicted error, right? This is that, and through that, this is the weight. So in the weight, you will see somewhere this is the phi IP, this is the phi IP, right? And this is the ANOVA kernel functions. So the ANOVA kernel functions will replace to the actual one. So this is the final equations, and I'm going to replace this to this. And then this time you will see to write in a smaller version. So I can write the phi dash and nu dash and like that. This is just assumption of that and assumptions of that, and then rewrite the same equations in this manner. If you can rewrite the same equations like this, then this is that, right? And if this is that, then you can say this is your what? The equations look like what? These equations are look like a state equations. State equations, right? X dot equal to ax plus by bu. Remember that one. So this terminology, this first term is known as A. A of the state transition matrix. So A matrix you can find out through this way. This term is A matrix, right? So if we have the A matrix, then we can calculate the eigenvalues for that. And if we have the set of eigenvalues, then we can go for the eigenvalue stability analysis, or we can go for the eigenvalues of the symmetric state transition matrix and describe the non-stationary system with the magnitude less than 1, then the system is asymptotically stable. So if you will use this theorem of the eigenvalues, and then try to find out all those diagonal elements, and then try to keep less than 1, then you will find this relationship in between these diagonal terms. If this is that, then again shuffle the equations, and then you can reform the equations, and then finally you will see this is the relationship where you will find the omega, and this omega is the learning rate. So finally you can say this omega, you should choose a omega in such a way so that this omega will be the bigger than with respect to this mu p. Mu p is the learning, autocorrelation factor which we will calculate. This is a calculated one. This is not a constant one. So through this way, we will choose a omega in such a way so that this term will be bigger than that. Right here, you will see the 2 omega. So one omega term is here, omega square, and another omega is here. So inside the code, we will select the omega in such a way that here, if you will again put omega value, this is a little bit higher or very higher or too much higher. Finally, I will say not too much higher, but the impact of the omega, if this is bigger than that, is not that much significant. Just it should be little bit higher. That's it. Not required infinity, or not required 1,000 and 100 times and 20 times. Little bit higher. That's okay. Otherwise, on the performance side, the impact of the different omega is very negligible. So we can ignore that. Okay. So through this way, we will select the omega value for that. Okay. Finally, this control behaviors tested on the different signals, as I told. So here we will this is estimation technique actually. So you can see on your screen this is your input signal, just signal, and then on that signal I've applied the same technique and tried to find out the estimated values. So you can see this is the estimated value. So this is your fundamental component of this signal, and then after that I will subtract this signal from this. The rest will be known as harmonic component. Right? So every signal has the 2 components, we can say, that is the fundamental component, and the rest all we can consider as a harmonic component. Definitely harmonics will consist of interharmonics also. So these are the harmonic components. So finally, we will calculate this one and subtract from this, and the rest all will consider as a harmonic component. So this several things you will see here. And this signal is 37.34% harmonic is here, right? So also on the experimental setup also, I tried to find out the actual fundamental component from the different types of signals. So this is the signal. So in these signals, this is the fundamental component. And for this signal, this is the fundamental component. This is a structured fundamental, but the fundamental component magnitude I'm talking about. This is not the signal actually. The signal wise, the same type of signals you will see. This is the magnitude of the fundamental component actually. In the signal side, exactly same frequency or same type of pattern you will see, same sinusoidal behavior you will see for that one, right? How I will get that? Simple, just multiply with UP, unit template. Simply, I will multiply with U, and then you will see the signal. The signal will look like very similar pure sinusoidal, right? This is that. Also compared with the different techniques, and then finally this comparative results show that this is more accurate and more stronger with respect to all other techniques, nothing else. Okay, so finally this signal extraction technique will include in our control behavior. So this was our actual layout and actual system, right? So in this system, how we will include that is the challenge. So this is the system, means we have solar panel, and then this is a DC link, and you can say this is a single stage. I have not used any DC-DC converter here, and then directly attached with your VSC voltage source converter, and then interfacing inductors, and then filters, and the loads and all. So you can see that. But in this system, this is single stage, and the 2-stage side you will see one boost converter here, this DC converter. The difference between both is rating of the panel. Actually, here I'm going to integrate with the grid. So grid voltage will be around 450. Suppose you are thinking for the line voltage, or if you are thinking for the phase voltage, so that will be around 220 and all. So if this is that, suppose this line voltage is 420, 450. So what should be the voltage here on the DC link? So if you want here, the voltage should be the 415, 420. So here on the DC link, the voltage should be 440 into root 3, and 10% we will keep higher because of this losses of the entire system. So we will say 1.1 into root 3 into 440. So you will see around this voltage will be around 700. DC link voltage should be 700. So here we are going to attach a solar panel. It means what? The panel voltage rating should be 700. Normally all the available panels modules, you will see the voltage rating 32, 42, 72, and like that, not more than 100 and all. The commercially available panels, right? But here required 700 means required number of solar modules, and we will attach all those modules in series in such a way so the MPP voltage should be around 700. Then only this type of system will work. But this type of system is okay, but only when you are going to generate a power or going to operate a panel on the large scale, right? For example, PV park and all, then that time this type of control will work, because that time you have enough amount of solar panels, and then you will attach all those in the series in parallel and then match the DC requirement, DC link voltage requirement. But normal cases, when you are going for the rooftop solar panel, then that time you have a limited solar panels. You don't have enough amount of solar panel like a 25, 30 solar panels, and then you will attach in a series and match the voltage. That time is not possible. I think possibility is not a big thing, but yes, it is not a general way. So that time you can go with the simple one DC-DC converter here. So that DC-DC converter, what will do? It will lift the voltage and match the DC link voltage of the solar panel voltage match with the DC link voltage. So the simple DC-DC converter we can use, and that is known as two-stage. This is single stage. So here the difference is very simple. It will depend on the ratings of that. Both have one merit, one demerit. Merit side here you can say this is a little bit the less number of switches is required here, right? So you can say the loss is little bit lesser with respect to the two stages, but yes, here the panel requirement is higher and with respect to two stages, right? So this is the merit and demerit. And also the another demerit is here with respect to two stages. Here, when suppose the 700 voltage on the DC link, this voltage is operating voltage. This voltage is the PV MPP voltage. So if 700 is MPP voltage, then what will be the voltage of panel means VOC, open circuit voltage of this panel. So definitely when you will calculate the open circuit voltage of this panel, that will become around 800 or sometimes 850 volt like that. So 850 volt open circuit voltage, right, of this panel. Then only you will get the 700 volt MPP voltage, operating voltage of this panel. So when you will select the switches here, so you will select the switch not for the 700 ratings. You will select the switch for 850 or 900 volt, because at equal to 0, when this panel will attach on the DC link, so that time that open circuit voltage will appear on this switch equal to 0 during the operation, right? So that time here the switch should be according to the VOC of this panel, means 850, 900 volt like that. But in the two-stage case, that time the panel will not attach directly with the switch. In between the switch and this panel, you will see one DC-DC converter. So that time these switches will select according to our DC link, or 5%, 10% up and down. That's it. Not like the VOC of the panel. So this is another issue, another difference between the two stages and single stage. Finally, come on the objective side. As I told, the objective is very clear in the single stage. All the objectives: source side objective, maximum power extraction; load side objective, DC to AC conversion, means the grid side, and the grid code matching, synchronization, means the frequency matching, phase matching, power quality of the supply voltage, and the D-state operation in the night. So all we will try to match, right? So all we will try to match. Okay. So so control side, if I will say the control side, so first of all, we will we will try to synchronize with the grid and try to solve the synchronization issue. So the first best option is we can go with the PLL. So we can use the PLL to find out the frequency and then we can match with that. But again, the issue with PLL is in the normal PLL, you will see when in MATLAB, you can find a MATLAB PLL block and simply you can use to find out the frequency and phase of the grid and you can use that. But in but once try to unmask of that PLL block and then see what is inside this PLL circuit, then you will realize that inside the PLL circuit, you have another PI controller. And that PI is tuned for a particular frequency, a particular signal. And but you are going to use that. So here, that PLL generates one lagging error inside your system, right? So for quick dynamic efficiency, for efficient operation, that PLL is not that much suitable. So here in this operation, PLL has not used. So what we have done, the here unit tempest based trick has used to synchronize with that. So simple way is that measure all those voltages and divide to the same voltage magnitude. So these are the voltage VA, VB, VC. So just multiply with the, so divide to the voltage magnitude. So this is the voltage magnitude. 2 by 3 VA square plus VB square plus VC square. So through this way you can calculate the magnitude of that. So if you will divide to the same signal with the magnitudes, what will happen? Here you will get a signal, and that signal magnitude will be high. Peak magnitude will be -1 and +1. For example, this signal, this VA is like in between -400 and +400 sinusoidal signal is VA. And just I'm going to calculate the peak, and then peak magnitude is suppose 400, and then divided to the 400. So what will happen? The signal will generate, which will be in between -1 to +1. That is known as, you can say, this signals are known as unit. By unit means unity is the magnitude. Peak magnitude is 1. That's what the name is unity. So then next, we will try to find out all those components as I told. So you will calculate the PV power and then divide to the voltage and generate the signal voltage PV component in the initial slides as I told. So calculate all those power and divide to the voltages and then see the signals, and then go with the single equations and take the difference as initially I told. So same thing we will do. We will try to find out all those components for the input terminals, PV components. So we will see the PV power, divide to the magnitude. This is the magnetic voltage magnitude. So PCC voltage magnitude also you can say that. So just multiply, divide to that, and then you will see the IDPP. Also, this is known as dynamic component, generated dynamic reflection component. Sometimes it's also known as PV feed forward component. Sometimes it is also known as PV current, PV AC equivalent current of the PV power, DC power. So different name you will see in the different literatures, but component is same. Another is the losses, as I told, calculate the loss power and divide to the voltage. So we will not do that thing here. What we will do, we will see the differences on the DC link. What the difference, what is the actual voltage reference, required voltage on the DC link, and what is the actual voltage on the DC link. So through this way we will generate the error, and this error will give to the PI controller. So this GPI means the proportional controller, the constant, and this is integral constant. So this is the PI controller. So just feed in the PI, and then you will get the DC link, DC link current component, or you can say DC link loss component. Another is the load component. So for the load, I will use the same estimator as you know, so Nova kernel trick. So we will use the same, means the load current UA, UB, UC, and zeta P. We will send to those code, what code I had discussed. So the same code we can use here, right? So all those components will fit to those code, and that code will give you the estimated fundamental component for the load. And then for the 3-phase, all these 3 load, add that and then divide to 3, and then you can say this is a net estimated active load power component for that. Right? So then again come back to the actual equations as I told. So initially, so just this is the loss component, this is your load component, and this is your PV component. So just take the difference. But in the initial slide I told, so you will go with this one and this PV component minus beta DC minus load. But here I'm telling we are going for the load and the loss, then minus to the I to PP. Why I am telling like that? Actually, the normal. If you look on the grid current or grid operation, then you will see when the power comes from the grid. So that time grid voltage and grid current both will be in the same phase when power comes from the grid. Right? So that time voltage and current are in phase. But when we are going to feed power inside the grid, means we are going to supply the power inside the grid, so that time grid voltage and grid currents are out of phase. So this out of phase means the minus, right? So this way, if this is negative, if this terminology is negative, it means what? We have extra power, and this power we will fed inside the grid. So that's in that way we can say that. So this way, if this is negative, then we will feed power inside the grid. If this is positive, it means we will take the power from the grid. So what we will do, this is what? This is the grid current reference magnitude only. So the magnitude, we will create a sinusoidal signals by simply multiply with the unit templates, because the magnitude is in between the -1 and +1. So if you will multiply this term with this zeta p, you can say all those issues will sort out. First is phase, because this signal generated from the voltages. So this all the voltages are already in the phase, so this will be in the phase. Another is frequency. All the voltages are already on the same frequency, whatever frequency means the true frequency, we can say that it means the not 50 hertz. This is 50.001. Then this UA will be according to that, because we have taken directly voltage signal from the grid. So the whatever frequency is there, this signal is according to that. So frequency matching is also solved here by using the same UA. You will see. Just multiply with that, and then we can say this is our grid current reference. If we have the grid current reference, then we will compare with the actual current. So this is reference, and then compare with the actual one. Then we will see the errors, and the error will go to the error. This is the generated one, right? So all these generated component, and then take the difference with respect to the actual one. See the errors, and the error will go to the hysteresis controller, and this hysteresis control will generate the pulses for the leg. So this is 3-phase, so you will see 3 leg, and then these are the signals for the different legs. So this is the basic controller for that, right? So you can see here on the screen, same thing what I discussed in the different equations, the same thing you will see here. So like that way we can solve the control action. Okay. So during the testing, this is MATLAB, but this is a hardware result. So on this screen, you can see this is a hardware setup to solve these issues, right? So here the same thing I've done, but during this, what we have done, we have taken the I will say the solar simulator, and then all the code is in the DSPs, and these are the sensors. In the inverter is this one, this is the inverters, and then again you can see all the interface inductors and the loads. So this way. So during this testing, the first of all, these things are tested on the under unbalanced linear load condition. Unbalanced linear load conditions means here you will see that this is the load current, and this load is linear. So this is the pure sinusoidal in nature, and this is a simulation result. So this is looking very smooth. And here unbalanced means at a certain moment one load gone, one phase of the load gone. So this is the load unbalance point when load gone. So in this situation, what is going to happen? If load term is going to disconnect, so load one phase load disconnect means what? The load current consumption will decrease. So you can see here the load current consumption decreases, right? So if load current consumption will decrease, then what will happen? Then the power, which is amount of power which is going inside the grid, that should increase, right? So you can see here it is increasing. But here, if you will look on this, and this both is downside, right? Both is falling. So in one look, you can say this is also decreasing, but this is not decreasing, this is increasing. Why this is? So this is decreasing. So if you look on the y-axis, then you will see these are the positive component. So 2 become 1, right? So this is the fall, 2 become 1 here. But here, if you look on the y-axis, here this is negative component. Suppose this is -16 becomes 17, -16 becomes -17, right? So that's why this is like that. Because as I told, the current is going inside the grid, so both are out of phase. Out of phase means negative current. So that's why this is negative. That's why this is the increasing. amount of current increasing, that's why this is downstream. Similarly, on the experimental setup, you can see the same thing, the linear load conditions, the diesel load current is the first one, the load current, and then one is load unbalanced conditions. Because of this unbalance, you can see here, the load current component decreases, and then grid current component increases. Again here, so you can see this is the axis line, so this is above that, it means this is positive component, this is axis line, then below that, so these are the negative component. So negative, in the negative domain, this is increasing, positive domain, this is decreasing. So like that, you can say that. And during the unbalance, voltage, DC voltage is almost okay, right? And then if you will go with the harmonic analysis, then you can see the PSD here. So grid current PSD is around 1.5%, and the load current is also 1.19%. Both are the linear, so no issue with that, and everything is working very fine. About the nonlinear conditions, so this is the nonlinear conditions. And also during the nonlinear conditions, I consider the unbalanced conditions also, means the highly nonlinear loads and the one phase load gone at a certain moment. Then again, the load gone means the current will decrease, and then the grid current will increase. And then, but the beauty of these things is the load is like this way. But if you look on the grid current, sorry, this is the grid current, then you will see this is purely sinusoidal. Come on the experimental side, when you realize this real things. So this is the load current, the green color, this is a hard, dark green color. So this is your load current, highly nonlinear current. But at the same time, the grid current is purely sinusoidal. Why this is? Because our inverter is generating the harmonics for this load. Right? So that's why if you look on the harmonics, the inverter current. So this is the inverter current, and this inverter current is not pure sinusoidal. This inverter current is not pure sinusoidal because this is the addition of grid current and this nonlinear load current. Because this inverter is generating current, harmonic current for loads and rest power as a pure sinusoidal for the grid. So this is the combination of both. That's why this is look like this way. So if you go for the harmonic analysis, then you will realize the grid current USD is 2% and load current USD is 27.3%. But if you look here on the inverter current harmonics, inverter current is 14.7% harmonics on the inverter current. So this is because this inverter is generating current for the harmonic current intentionally for the nonlinear loads. Okay. Similarly, the same thing tested on the grid voltage fluctuation conditions. So you will see that the over voltage conditions, under voltage conditions, when the voltage is fluctuating. So what is going to happen? If we will see that if over voltage conditions, the voltage will increase on the grid, or under voltage conditions, the voltage will decrease, then what will happen? Then current will also change accordingly, right? Over voltage conditions, if the voltage will increase, then current will decrease, grid current will decrease. If under voltage, grid voltage will decrease, current will increase, because the power feeding inside the grid is constant. So all those components will also according to that. So you can see here, so how the things are changing. So you can see here all the components, how it is changing. Similarly, you can check on that. So this is for the over voltage and under voltage conditions. So here you can see this over voltage condition, voltage increases, here voltage decreases. So voltage decreases, grid current increases. Here the voltage increases, the grid current decreases. So if you will go for the harmonics, then you will realize that in the normal condition, it is 2%, normal conditions, but during the over voltage condition. So during the over voltage conditions, the grid current decreased, it means your harmonics will increase. So this is for the over voltage conditions. So grid current magnitude decreases. So normally this was the 5.8, but this time it is 4.9. So the grid current magnitude decreases, harmonics increases. Same time here, the grid current increases because of the under voltage conditions. So you will see here, the voltage current magnitude has increased. So this component has decreased because harmonics TSD calculations. What is TSD? If you see that, think that. So simple is that all the harmonic component divided to the fundamental component multiplied with the 100. So, or you can say the percentage of harmonics, all harmonic component with respect to the fundamental is your TSD, right? So here the denominator is your fundamental component. During this over voltage conditions, denominator is decreasing. If your denominator will decrease, then definitely the ratio will increase. And in this situation, if the denominator is increasing, so automatically the ratio will decrease. So that's why this is. It not mean that your harmonics is increasing, but because of the denominator component changing accordingly, that's why your harmonic percentage harmonic number is changing. Okay. This is the situation. Then also for the solar side, solar irradiance are changing. Then how these things are going to change. Solar irradiance change means here you can see that 1000 to 600, here 600 to 800. Solar irradiance are fluctuating, going up to down and down to up. So this time power is also changing accordingly, but the load is constant throughout the day. So if load is constant, then all the variations you will see on the grid side. If this solar radius gone down, power generation gone down, so you will see that the grid current magnitude gone down. But same time, if it is increases, then grid current magnitude will increase because load will take the same power throughout the day. So this is the situation. Similarly, on the experimental setup, you can see that the components are similarly going down and up according to the situation, according to the condition, right? Finally, the main point under voltage, under day to night mode of operation. As I told, in the night time when the system solar irradiance will be 0, then that time the entire system will start working as a statcom or d-statcom according to the conditions. So here we have local loads, so we will operate as a d-statcom. So you can see that during the daytime when the solar radiance is 1000 watt per meter square, here to here 0 to middle one, so 0 to 0.5, here you will see. So this is the generated volt current, grid current, load current, and all those things. And in the night time when the solar radiance is 0, so that time you will see PV power is 0. If the PV power is 0, so that time this VSC, voltage source converter, if you will look on the waveform, so this is the waveform. It means what? So this side, this time, this voltage source converter only generating nonlinear currents. Nonlinear currents for this load. Since we have a accurate estimation, so according to the estimated harmonic requirement of this load, this highly harmonic load, so this side, this you see, the inverter is generating pure harmonic current, right? And then only fundamental components coming from the grid. So you can see this, if you will add this and this component, then this will generate. So like this way. So nighttime, who is feeding this current? Grid is feeding, but this is a nonlinear current, but grid is feeding pure sinusoidal. This is called the supportive behavior because all those harmonic burden is on the inverter side. Inverter is doing those tasks. Similarly, night to day mode means the early morning, how the things is going to happen. So you can say that this is the nonlinearity, but once the solar radiance increases, and then it will change the mode and go on according to that. Similarly, if you go for the harmonic analysis in the simulation side, so you will see that in the night time mainly, this is the grid voltage and the grid current. Grid current is the, I think, 1.2%, but the load is 29%. But here, the inverter side, ideally, inverter is only generating the nonlinear current. So the TSD should be what? Ideally, this should be the 100% because inverter is only generating nonlinearity. So this is the TSD equal to the 95.42%, right? So this is that. Similarly, on the experimental setups, you can see that the day to night mode of operation during the day conditions. So the grid currents are sinusoidal, the voltage is like this way, and then this is the load nonlinear loads, right? In the night time, you will see here that during the night time, only harmonics currents are generating through our inverters. So this is that, and then because of this harmonics current generation for this load, this grid current is pure sinusoidal. But one thing you can see here, how you can say that the daytime the power is going inside the grid, but in the night time power is coming from the grid. So you can see the phases here, as I told. So here, if you will see the phase difference between the grid voltage and grid current. So this is grid current and grid voltage. If you will see here, the both are out of phase. Grid voltage downside, grid current upside. Similarly, so you can see that here you will realize that the phase difference between the current and voltage both out of phase. But in this situation, if you will see here, in this situation, both are in phase. Means in the night time, who is the source? Grid is the source. So the both voltage and currents are in phase. right? So the power is coming from the grid. So this is that. But this is the mode change conditions, meaning where the mode is changing one to another. So this time your DC-link capacitor will help, right? So that's why you will see that the slightly voltage, DC-link voltage has gone down, but again recovered quickly. So this is the situation. This is a mode change duration during that. But the load side, I will see the user, I will see the user uh, comfort not going to compromise because the load current is throughout the journey is constant, day or not, whatever. And the grid side, if you will compare, if you will calculate the grid side, grid is also smooth and the no harmonics. Right? Similarly, night to day, in the early morning when the solar radiance is going to increase, then the PV current is also slightly increasing. Then what will happen? Then this is the mode change. During the mode change, slight mode change, and then again starting changing the operations. So during this side, the current was coming from the grid, and during this time, current is going inside the grid, like that way. So this mode change automatically it is happening, or we can say seamless mode change according to that. Okay. So if you again, if you will go for the harmonic analysis, then you will see here in the night condition only. In the night, the current is the 3.1, the load current is 27.5%. But for the inverter side, it is 94.7% harmonics. Right? It means the night time only harmonic currents are generated from the inverter. Same if any disturbance is on the grid side, then what will happen? For example, on your screen, you can see this is the grid voltages, three-phase grid voltage, and this is unbalanced grid voltage because of any fault in the grid. So what will happen? So you can realize here the three different voltages for the grid voltage. So this is that. But grid side grid voltage have unbalanced, but the grid current have purely balanced current. So you can see the grid currents are purely balanced. If you see here the phasor diagrams, then also you can say grid voltage on balance is 26.11%, but the grid current is balanced and the unbalance in the grid current is totally negligible, close to zero. Right? So this is the beauty of this controller. So this type of controller will also take action during the grid side disturbances also. Not only the unbalance, suppose some during the weak grid conditions, if some harmonics is in the grid voltage, so that time also this will not propagate those harmonics in the load current. Sorry, feeding current of the grid current. It will not propagate in that. But here, the push, I'm not going to solve this grid issue. And balance is there, and always it will be there because this is a big issue. It will solve only through the huge reactive power. If you are capable to generate huge amount of reactive power, then only we can sort out this voltage issue. But here we are going to operate in a active power generating mode. So here we are not going to contribute in the grid fault, but we will continue our power generation inside the grid. It means as a source, as an active balanced source, we are going to act here. So this is the situation. This is for the three phase. Similar type of thing also you can see, you will see in the single phase. Only differences will come. The number of pulses will generate here less, or number of component will be less, nothing else. So you can use the same controller for the single phase also. But yes, one thing I will say, in single phase systems are mainly for the household operations. So for that purpose, we cannot go with a heavy controller, mainly I will say, because heavy controller means your requirement will be a heavy DSP board. So that is little bit costlier one. So that type of thing is good for your big plant. But for the household, required a smaller one and a small DSP, a small kit, a small controller board. So the smaller controller board means that the controller algorithm should be smaller because the control board size depends on the requirement of the cache memory. Means the processor, whatever processor we are going to use. If you are going with a heavy controller, then definitely the requirement of cache memory will be bigger. So that time in the three-phase system where we are going to play with a huge power ratings, means hundreds of kilowatt and all. So though for that conditions, three-phase heavy controller is okay for that purpose. But for the grid condition, for the single phase system, that is not the right way. So we can go with the cheaper one also. So here I will show some cheaper controller also. So that here requirement of the computational cache memory will be lesser, and then control algorithm will be a little bit simpler with respect to that. So this is for the single stage, but side by side also I will try to show here the two stage behavior. So this is a single stage. So just assume that you don't have a large PV panel. So here the PV rating, just assume that the PV rating is smaller. So in this situation, how it is going to work? So in this situation, I have used the one DC-DC converter, because here the requirement of the voltage will be somehow here something different. For example, here suppose you are going to integrate with the grid. So the grid voltage will be 200 around, right? 210, 220, and the requirement of DC link will be 210, 220 is the grid RMS voltage. So we will multiply with √2 for the peak voltage, and then multiply with 1.1 for 10% higher because of the just for all those losses and all. So if you will calculate like that way, so you will see this will become around 350 volt around on the DC link, right? So this is that. So if this 300 volt or 350 volt and 400 volt suppose you want on the DC link, so again this is a big task for a solar panel, right? So if you have a limited solar panel, so we can use one DC-DC converter, and that will boost the voltage and match the DC link voltage. Simple. So this type of concept has used here. Right? And again, you will see the control objectives, two set of control objectives you will see. This set of control objectives, maximum power structure for the DC converter. And then grid side, you will see all those DC AC conversion, harmonics, and power quality matching, and all those grid code synchronization all will go through the inverter cycle. Control strategy will be very similar as I told initially. The same thing you will see here again. All those PV power and then grid power, and then we calculate the losses and the load current. Same thing, same slide is here also. Nothing changed here. Only how we will calculate these components will be maybe changed, right? Nothing else. Mainly this component, the load current component, because here previously I had used the one heavy estimator. So but here I will go through the smaller one, a small filter. So this component. So this will be a little bit changed. Here you will see the little bit change. The rest all will be same. Same DC link components. We will calculate the errors, difference between the DC link voltage, and then fit to the PI controller and generate this one. Similarly, for this one, we will calculate the PV power and divide to the grid voltage magnitude, and then we will say this is the IDPV. So all will be same. Only this component will be changed. Nothing. And again, as I told here, the two control actions you will see. One control algorithm for the DC-DC converter. So what you will do, you will sense the voltage and current simply by using any MPPT technique. You can generate the VREF, right? And this VREF and compare with your DC ref, DC voltage ref, and then go with the duty ratio calculations, and then this duty ratio will be your beta, and then this beta is the duty cycle mainly you can say. And then go with the pulse generator, and then generate the pulses for your boost converter. So this way, and this DP ratio calculation based on the converter, what type of converter we are going to use. For example, in this picture, in the previous picture, we are going with the boost converter, right? So in the boost converter, what is the relationship between the input voltage and output voltage? So you can say simple input voltage and output voltage relationship is output voltage equal to the 1 divided by 1 minus D into B input. So B input means B PV ref, and output is VDC ref, and simply so this way we can calculate the duty cycle, and that is that beta, and we can pass to this way. This is the one way. Another way is also, so the issue of the P&O also you can solve here. So this issue with the P&O is step size. Normally when you will go with the P&O or INC, then always you will see the fixed step size is the issue, and then 3-step oscillations type of issue you will see that. So you can solve that issue also here. What you can do, so this is your VPV ref generated, and then what you can do, this is your VPV ref, and then this is your actual VPV. Take the difference, VPV ref, and then this is VPV. Take the reference, and then this reference calculate the error. This is actual voltage, this is the reference voltage. Calculate the error and give those error to the PI controller, and then output of the PI controller, just assume this is your duty cycle, like that way. So you can solve the step issue also. So both you can go for. Another is the inverter side, as I told. So what you will do, calculate the VDC ref, an actual DC link voltage, we see the error and give those error to the PI controller, and that will be the DC link, loss component, right? Another, as I told, so go with the PV power, calculate the PV power and divide to the magnitude, then that will be the your PV feed forward component or PV dynamic component, or different names for this component. Another is the load one, right? The load simple one. Here we will not go with the ANOVA kernel one, stochastic one. Here we can also use the DAVF. This is a type of filter. This filter we can use here to estimate the fundamental component from this nonlinear, highly nonlinear load current, and then we can use this one here. Also the same thing we can use for the grid voltages also. Suppose this is a single phase, so this here the grid will be sometime weaker. So grid is weaker means you will see the some harmonics also in the grid voltage. So what we can do, we can use this filter to filter out this grid voltage, and then pure voltage or the pure grid voltage we can use here for unit temperature generation or magnitude calculations. We can use that one. So two components will become, this is single component VS, then you will fed here, then you will find the two component, the K dash and K double dash. The meaning of K dash is in phase component of this VS, and K double dash is the you will see the 90-degree phase shift, or we can say the quadrature component of this voltage, simple, just like alpha beta. So this is the in phase component, and this is your quadrature component of this signal. So this is that. Similar for the load also. This is a load current, and then this is your in phase component of the load current, and this component is the quadrature component of the filtered signal. And simply you take the root under this, and then you can say this is the magnitude of that filtered fundamental component, and like that you can use right. Similar things as I told initially. So same beta, and then beta is the you can calculate because the input and output voltage relationship. So by using the boost converter concept, simple you can calculate, because V PV ref V output equal to the 1 divided by 1 minus beta into VDC input. So that is that way you can calculate that. Grid voltage magnitude, initially the quadrature component square plus unit plate square, and then simply you will get the peak voltage of plant. If you have the peak voltage, then divide to that, then you will see the UP and UQ. So if you will divide here to the peak magnitude, then you will see this is the unit template in phase component. And if you will divide this component to this, then you will see here quadrature component of that. So this way we can calculate that. Similarly, PV dynamic reflection component, the feed forward component, PV power divided to the magnitude, simple. And then loss component, right? See the error, and then pass this error to the PI controller, and that will give you the your DC loss component, as I told. Similarly, for the load also, if you will pass the load to the filter, and then the filter will give this and both component, and then you will take the ratio. This is the amplitude of that. If you have that amplitude, then you can go with this relationship. This is the PV input power, these are the losses, this is the load. So you can see here that this is a negative or positive. If this term is negative, power will go inside the loop. Positive come from the loop, like that way. So whatever this is we can say this is the grid current reference magnitude. Same this grid current reference magnitude multiplied with the unit temperature, and then you can value this is grid current reference, like that way. Same thing what I discussed. So you can see here. But the question is this filter. What is this filter? Then we are not going to use the Nova kernel. Then what is this filter? So this filter is known as decoupled adaptive vectorial filter. So this things we can use here. This decoupled adaptive vectorial filter means here what we will do, whatever voltage we have, so we can use the clock transformation to change in alpha beta component for 3-phase system. But if you have a single phase system, so that time this alpha beta component is considered as a whatever voltage we have, the grid voltage. So we can say this V alpha equal to the V grid, and then V beta is the V alpha phase shift 90 degrees. So intentionally we will create a phase shift in the grid voltage, and that will consider as a V beta. Simple. In single phase component, single phase conditions, this clock transformation will not use. And this class transformation will not use directly. We will consider input voltage or input load or input signal is a alpha component, and give the 90-degree phase shift and consider as a beta component. Simple, no transformation. But in the three-phase, we can go with the transformation also. After that, we will go for the cross coupling. So you can see the cross coupling. Cross coupling, during the cross coupling, what we will do, we will apply the actual omega. So what is the actual omega that we will apply here. And in this situation, you will see one constant is that Kf. This Kf is the gain constant, and then we will do accordingly. So finally, if you will do these things, then you will see that alpha dash and V beta dash you will get. This is a V alpha dash and V dash. So we will again generate V alpha double dash, V beta double dash. So how we will generate whatever signals we will get here through this integrating circuit. So this simply we will give the 90-degree phase shift intentionally again. So this is the 90-degree phase shift intentionally again. So if we have the two signals, V alpha dash and V alpha double dash, so we'll take the ratio. So take the difference and divide to 2. So we will say this is the V alpha triple dash. Similarly, V beta triple dash. So this triple dash will calculate. Yeah. If we have these two things, then what we will do? So this in this situation, if this is three-phase, then we will go with the inverse Clark transformation, and then we can generate the ABCD. But if this is single-phase system, then V alpha triple dash will consider as a input component, or you can say the filtered signal, and this V beta triple dash will consider as a quadrature component of the filtered signal, no inverse transformation there. Right. So this is the picture. This is the picture of that. So here two signals. So single phase direct add here and give a 90-degree phase shift and add here. Simple one signal. Rest all will automatically calculate according to the blocks. All those blocks I will already discussed, and then you will see that these signals. If this is single phase, then this will be the your filtered fundamental component of the signal. So this one. So, but as I told here, we have one component Kf. This is the, you can say this is the parameter of this filter. So this, how you will decide the actual value of this Kf. Simply we will go with the stability analysis, and then we will see what is this. So the stability analysis technique, you can go with the any technique. I will say you can go with the any technique, and then you can decide that. Simple way is that you can go with the transfer function, open loop transfer function, and then try the Routh-Hurwitz technique, and from that you can get this one. So when you will calculate the transfer function, that time you can take this integrator as a 1 by s, right? And then omega equal to, you can take the constant number 2 pi f. Simple, if you know the grid voltage, grid frequency, simple, this is a constant number. So easily you can calculate the transfer function and then apply that Routh-Hurwitz and then find the K. Simple. It is also simple way. Another way is also you can choose the settling time, draw the signal and then see that, fix the settling time, how much settling time you want, and then accordingly you can calculate that way. So this is also one way. So according to the signal propagation, signal behavior, you can calculate that way also. So this is not a big issue to calculate that, right? So the simple, simple, we will go with all those equations, reshuffle all those equations, and consider, as I told, all the integrator as a 1 by s. And then if you go for that, then you will see, so V alpha dash and V beta will look like this way. And if you have these two signals, then you can generate the alpha dash and beta dash through the 90-degree phase shift. So this is the 90-degree phase shift. 90-degree phase shift means what? Means you are going to give the delay, intentional delay of 5 milliseconds, right? So this is your e to the power minus 0.05 is the 5 millisecond intentional delay you are going to give in this. If you will give this, then you will get the V alpha double dash, V alpha, V beta double dash, and then take the difference and divide to 2. So this is your triple dash. So this is that. If you have this one, so this is the final transfer function. You can say that if this is the final one, then you can put all those equations. Then finally it will look like this way. If this is the final matrix, then you can go with the transfer function. So what you will do, just take the determinant multiply this one and subtract this one and equal to 0. That will be known as your transfer function, or we can say the open loop transfer function. So this open loop transfer functions, so we can calculate the characteristics equations just equal to the 0, And this time, for the simplicity, you can take this one as a 1, then rewrite the same equation like this way, and omega will consider as a 3, 1, 4, right? So you can rewrite the same equations in this one. If this is the equations, then you can go with the root for the stability analysis, and then you can check this is the stable or not. So this is the way. So this way, if you want to value of kf, so don't remove this. Keep kf here, here, and then here. Then you finally keep try to match, make all these numbers positive, and then you can find the actual value of kf. That is also one way you can go for that. Now finally come on the all the results. So again, the results will be, during the results we will take the different cases. So for example, on your screen you can see the normal operations, right? So during the normal operations in the nonlinear current, nonlinear load conditions, so you can say that this is a 7% nonlinearity is in the load. So this is the load current. So this is 7.7% in the nonlinearity side, right? But the grid current is sinusoidal, and this is around 4.3% like that. So this is your grid current. So this way you can say that. Also the PV power fluctuations, when 1007.5, then what is going to happen when this grid voltages are fluctuating, then you will see the different types of signal will go ups and downs according to the power, nothing else. Similarly, for sudden load unbalance, when suppose load goes 0, so if load goes 0, then what will happen? The total current will go inside the grid, simple. So you can see these signals, grid, all the load current is 0, so the only the PSC current is sinusoidal, and this is also pure sinusoidal. But here, this is not pure sinusoidal, because this time this is the addition of this and this. But this time this is pure sinusoidal, because the only active component is going inside the gate. Yes, the active power is going inside the gate. Similarly, under voltage over voltage conditions, so you can see that the voltage is increasing. If the voltage is increasing, current is going down, just like the previous one, nothing else. Similarly, day to night mode of operations, here you will see that this PV power is going to become 0, PV current is going to 0. So the mode change you will see, but the both are pure sinusoidal. Both mode changing, but the sinusoidal nature is not going to change here. Similarly, here in these situations, so when this is going to 0, so the only nonlinear currents are coming from the inverter side. So this is nonlinear currents. The loads are pure sinusoidal, pure nonlinear. Similarly, night to day mode, this is the situation. Mode changes here. Both sides pure sinusoidal. Then like previous one, nothing else. And then finally, on through all these conclusions, I can conclude that here. So according to the different situation, right? According to the different situations and the different processor, we can choose the different techniques for our system. For example, three-phase system, you can choose the first one because there is a serious harmonics issue with your local loads. But in the single phase conditions, when you have a limited loads or local small loads, so that time this filter is also capable to do all those things. The filter means what? This is simple band pass filter. But again, you cannot go with the simple traditional band pass filter, because in the I will say the traditional band pass filter means the filtering capability depends on the order. If you want to filter out all those signals and then pure signals, then it will increase the orders of the filter. Order of the filter means you are going to introduce the lagging, right? So means the step delay you are going to. And as I told, this is a pure sinusoidal signal, so delay is a bigger issue here. How we will sort out those delay issue? So this way you can select your filter accordingly or control behavior accordingly. And the heart of this controller is mainly this type of inverter-based controller is the estimation of your local components. Here I'm going to sort out those local nonlinearity. So that's why here load current estimation was the key issue. But at the same time, suppose you don't have any load and directly you have attached with the grid. So that time grid voltage estimation is very serious issue. How you will estimate the voltage issue, and then according to the voltage, you will decide the amount of reactive power and see your capability of the filter, and then you will generate that amount of reactive power and fed inside the grid. Definitely, the grid is a big thing, so we cannot generate hundreds of MVR and fit to the grid. But yes, according to your inverter capability, you can generate the reactive power and support the grid in the night mode or the day mode also. So this way you can use that. Okay, so thank you. If you have any questions, you can ask. I will be happy to answer.
Thank you, sir. Nishant, sir, thank you.
Thank you.
You have given an effective lecture for grid connected as well as we can say single phase or three phase with various control scheme. So this lecture, I think it will be helpful for those who are working in this area. So from participant side, if you have any such type of queries, you may ask here. Welcome.
Good evening, sir.
Good evening.
This side Kumar Singh, sir, doing PhD under Dr. Shivam, sir. And I am working in the same area, sir. And I have read LMS, LMF, second order generalized algorithm, and proportionate affine projection algorithm. But sir, this algorithm is some type new and very effective. Sir, I want to know that if you want to implement any controller, then what factors should we consider while selecting the controller, and what controller should I choose so that this controller will be effective for my work?
Yeah, good. So controllers, always you try to find out the two things. So one is the complexity, right? So complexity should be less, but if you are going for any LMS or LMF, definitely you will find some complexity there. But mathematical complexity is not a big issue nowadays because we have a advanced processors now. So this is not a big issue in your control. Just always try to find out the delay, how much delay you are going to face during your calculation. So delay, the major delay components are differentiation, right? Always try to avoid the different any type of differentiation in your controller. Whatever controller you are going to select, just see is any differentiation component is there or not. If there, definitely you are going to face a heavy delay on that delay. So just leave that. Integrator sometime okay because integrator not introduce huge delay. Yes, one step delay, but different type of you will found delay removal techniques already available in the literature. So we can introduce or we can inject that to sort out the issue with the integrator. For example, in the single phase, I have shown the controller, but you will see the two integrator was there. So again, you can say, yes, one step delay is going to come because of that integrator, but no, this I will say we can counter that because the one feedback loop is there for the integrator and then we can sort out that. So delay, the first your target should be the delay. So try to remove the delay issues. So delay should be the minimum with respect to any condition. So that should be your first priority. And then second time you can go with the requirement of cache memory, requirement of your different type of memory and all. So that should be the secondary requirement. So this way you can select what filter you are going to choose, what technique you are going to choose.
Okay, thank you, sir. Sir, can you please share some sources from where I can get the knowledge about these latest controllers?
Sources, the latest means directly the IEEE Explorer. Simple, you can go with that, and then I also read from there. So simply put the title and few keywords, and directly you see the latest paper. One key suggestions I will see, try to find some journal papers, for example, transition paper. So that will be the more effective with respect to the conference paper. I'm not telling the conference is not that much effective. Conference is also effective, but the conference have limited page size, right? 5 pages or 6 pages. So in a conference paper, you will not see that much of description, discussion and derivations. But in the journal paper, you will find all those detailed descriptions, discussion. So like that way. So I will suggest go with the journal papers and latest journal paper, mainly early access. So that will be the more helpful for you.
Okay, thank you, sir. Thank you very much. And at last, I will request you to please share your mail ID or any contact info so that we can contact you, sir.
Mail ID is not a big issue. Simple, type my name, Nishant Kumar, and @itj.ac.in. Also, you can write my name on the Google, you will see the portal and easily you can find. But yes, I will say here, no issue. No issue. And one thing I will, you are a PhD student, I will say that. So don't go only with the controller and then try to find out a new controller. I will suggest that go with the features. What extra features you can introduce in your controller, right? So this is also one area where you can work, right? So that for example, suppose a fault occur in the grid, so your controller should sense the situation and then cut out from the grid this type of features. Means any other features also. Means suppose now electric vehicles are going to come in the market. So electric vehicles are going to come in the market. It means, you know, what is going to happen. For example, what you are PhD student telling. So see here in this picture one mainly. So this is the electric vehicle and this is the charger, right? Simple way you can say this is a charger, means the AC to DC converter, and then DC power is going to charge the battery of the electric vehicle. Simple word we can say like that. But in reality, it's not like that. If you will think about the any car, suppose car, so that time this is not only the AC to DC converter. This is not AC to DC converter. This will come with a BMS, battery management system. So what is that? You will see a communication channel in between. So here, according to through the communication channel, this converter will extract the current according to the battery conditions. Suppose battery have a particular temperature, suppose battery is heat up. So that if battery is heat up, then you will see that the current requirement is huge, and suddenly after the certain time, when battery will cool down, then that time this current limit will increase. Or sometimes you will see the step charging behavior. Initially, the battery will take the huge current, then after a certain SOC, the battery current will go down and then again down and down. So this type of things you will see them. So and this information will come from the BMS of this electric vehicle. So you in your controller, you can make a provision so that the BMS command you will collect from the vehicle, and then you will try to generate the current from this controller or from this inverter according to the command given through the car. So this feature also you can include in your controller. So different features try to include in your controller. So that is the one area.
Thank you, sir.
Yeah, thank you.
Okay, thank you, Miss. Next one, maybe anyone can ask here. Nishant sir, meanwhile, I want to introduce in our department, electrical engineering department, senior professor here, LM Saini sir is also with us.
Hello, sir.
Yeah, thank you, Shivam.
Yes, sir.
Yeah, it was a very nice lecture by Nishant, and particularly case studies were very good in different conditions. Were very informative.
Thank you, sir.
Yeah, very good, Nishant, for sharing such a knowledgeable concepts here with all of us.
Thank you, sir. Sure, one day we will get the chance, then we will meet the physically also. So this is online. So
Yeah.
thank you for your kind words. Thank you, sir.
Yeah.
Thank you, sir. Thank you, sir.
Yeah.
Any one question can put up here from audience?
Hello.
Yeah, Collins. Yes.
Please, I would like to ask for those of us who are new to this kind of control design method, what is the background that we need to be able to understand this control system? And secondly, how long will it take me to learn this control system? Thank you.
It will not take too much time. Mainly, I will say see, first the initial thing is that when you are going for the control technique, so first decide your controller is for what. If you are thinking for a controller for a one inverter, an inverter operation means suppose this controller, this is for the UPF operation, means your task is to generate the active power and feed in the grid. So for this way, this is very important. Sometimes if you think only for the grid integration solar and then all, then you will confuse. First to decide what is your initial task. So for this one, or suppose you are thinking for the virtual plant generation, or suppose you are going for the reactive power support, suppose you are going for the grid feeding grid generation, and the different type of behaviors. So first select the behavior, which for what behavior you are going to operate. So this is the initial task, and choose one. And then for that purpose, if you go start reading the papers, basic papers mainly, or basic controls. For example, if you will jump on this control, you will confuse. Go with the basic control. What basic control is DQ control. Try to understand the DQ and try to implement that. This is a very commercialized control behavior, DQ control. Easily, so many literatures are available. In fact, the MATLAB models are also available in your MATLAB also. So directly you can see from the examples and then try to think or read the papers. So what is happening in different components. If you will be capable to understand the basic first controller, then after that, all the changes in the advanced version easily you can understand. And it will not take too much time. I will say the 1 month is enough for anyone.
Okay. Thank you, sir.
Okay, thank you, Collins.
Yeah, thank you, sir. I'm okay.
Okay, anyone next? Okay, so Nishant sir, it is already over. So, sir, I want to ask one question here.
Sure.
If we are going to connect grid connected mode, so if you see in the literature, there are various controller schemes. But thing is that if you want to make research, which technique will be better? So how to decide this? Can we make comparative analysis? Then we will discuss, and how to make outcomes from the behind the controller schemes.
See, definitely in the literature side, if you think so many controls are available, but the first thing, as I told, so first you try to finalize your objectives. So what is your key objectives? So because of several group of control you will found for the UPF operation, for your, as I told, the group control section, right? For the multiple inverters. Also, the nowadays you will see the coordinated manner of the control. Coordinated manner means the two inverters are communicating with each other and then working together, right? So these are the next step of the research. So two different inverters are going to communicate and create a virtual grid. So in these situations, you have multiple options. Means the delay in the communications. So if some delay, then how your controller will act. So this is the first thing. Second, you can say some cyber attack aspect is also going to come here. Means that suppose the information what coming from the first inverter, that is suppose malicious or maybe some wrong information, then how you will estimate that information are correct or wrong. So these type of aspects are nowadays coming in the control side. So you can look on those areas. So these are the recent areas where you can work on that. Similarly, also I will say the digital tune-based control techniques are also coming in the market. Digital tune means what? So you have a physical system, right? It means the actual plant, actual PV panel, actual inverter on your rooftop or on a park, and you have a mathematical model also. And now in between mathematical model and your physical system, both are communicating with each other through the communication channel. You are collecting different. You have placed the different several sensors and collecting the information. And through the mathematical model, you can analyze what is going to happen on the plant. So through this way, we can analyze the fault on a very initial stage. Right. So this is also one research. Mainly this type of research is going to come for the floating solar panels, means in the ocean region or on the river side, you will see the floating solar panels. So fault you can analyze on the initial stage. So this type of things are new in the control, so you can look on those things.
Okay, thank you, sir. Thank you. So there is one again question from Collins. Please, sir, what is the best type of controller for the boost converter?
Controller for the boost converter. The controller for the boost converter have one single switch, right? So you can directly if you have the information about the output terminal, what amount of voltage you want on the output terminal. So through the simple calculations, you can calculate that. And if you will say that give the name of that, then you can give any name. But if you have the output terminal voltage information, then according to the input, you can directly calculate the voltage, calculate the duty cycle, and then go with the pulse generation, and then you can trigger your switch accordingly. So I don't think here required any complex control technique for a boost converter. But yes, boost converter is going to come with a UPF operation, right? For example, you are thinking for an electric vehicle charger, and the charger is based on the boost converter, and then that time this boost converter is also associated with a UPF operation, unified power factor. So that time some control technique will be required. But a classical boost converter not required any complex controller. Simple calculations, you can solve that.
Okay, sir. I hope Colin will be satisfied. So by these question answer, we want to conclude here, sir. This answer, and especially in our honor, respected Elim Sani sir. So we want to conclude here, sir. Thank you.
Thank you, sir. Now I'm recalling Sani sir name. Several times I have heard during the IIT Delhi journey. Now this thing came in mind. Yeah, several times I have heard his name, sir's name from several times I have heard. Now I'm recalling this thing.
Okay, thank you, Nishant.
Thank you, sir. Thank you, all participants. Now we want to conclude. Over to the session. Thank you, sir.
Thank you.
Thank you to everyone.